Alrighty, part 3. Let's just go ahead and jump into some examples. Let's say I'm given f of x is equal to 8 minus root x, and we should know approximately what that means, or what that looks like. And I want the area that is bound by this, which of course is the parent function, reflected and moved up 8 units. This is the parent function. And then, of course, I want the area between these curves and bounded by the y-axis, okay? So you just got to remember that this means y-axis, okay? Well, I've gone ahead and graphed it for you. It looks something like this. We see this upside down radical function is the 8 minus the square root of x, because it has been, notice that if this is the parent, it was reflected and then moved up 8 units. I see the fact that there's this area right in here between 0 and what looks like 16 down here. We'll go ahead and we'll confirm that, but it is 16. And so if it's the area bounded by the y-axis and these two curves, my limits of integration should be 0 to 16. Let's go ahead and look at that really quickly, okay? Let's go ahead and set f and g equal to each other. When I add root x to both sides, I'm going to get that, and then I'm going to square and get x. So that tells me that I'm looking at 0 to 16 for my interval, okay? Now, on that whole interval, I recognize the fact that 8 minus root x is going to be the one on top, the more positive one. So 0 to 16, 8 minus root x minus root x dx. 0 to 16, I know that that's going to wind up being 8 minus 2x to the 1/2. Okay, and then of course from there it just winds up being 8x minus, well, when I integrate that, it becomes x to the 3/2 over 3/2, or 2/3 when you sort of take it out from the denominator. So 2/3 times 2 is 4/3 x to the 3/2 from 0 to 16. Great thing about the 0 is I really don't have to worry about it. So it's 8 times 16 minus 4/3 times 16 to the 3/2. Now, what is 16 to the 3/2? Remember, when you have a fractional exponent, you want to do the root first. So that's the square root of 16 cubed. The square root of 16 is 4. Cubed is 64. 64 times 4/3 is going to be 256 thirds, okay? Now 8 times 16, that's 2 cubed, that's 2 to the 4th. We already know that that is going to be 128 because we saw that in a previous problem. If that's 128, 128 times 3 is going to be what? Well, I know that it's going to be 125 plus 3, and both of those tripled, right? 125 tripled is 375. 375 plus 9 is 384. So it winds up being 384 thirds minus 256 thirds. And of course, we can wind up doing that relatively easy, okay? That's going to be 44 and 84, which is going to be 128. So it winds up being 128 thirds. And that winds up being our area. Now, if we want to go ahead and confirm that with the calculator, we can, okay? All we have to do is go ahead and plug in 8 minus root x, and then, of course, root x. And I put those into y3 and y4 respectively. And then we just gotta go ahead and go to the main screen. We'll integrate from 0 to 16. That's going to be y3 minus y4 with respect to x Come on. Okay. Now, that looks like it's going to be an approximation, so we'll make sure that our approximation is good. And notice that the algorithm in the calculator, like I said, even though it's imperfect, only differs in the 7th and 8th decimal place. So we recognize the fact that it is 42 and 2/3, and that's going to be our answer. Okay. Now, that was easy enough. Let's go ahead and move on to one that's perhaps a little bit more challenging. Yeah, this one's a little bit more challenging. This one ought to be a little bit of fun. Okay. Let's say we have f of x is equal to the square root of 1 plus x cubed. That ought to be an interesting looking graph. We already know its domain just by looking at it. Its domain is going to be from -1 to infinity, because basically you can have a negative cube. So if I plug in values to the left of -1, it's going to be 1 minus a negative number greater than -1. So it's going to wind up being a negative radicand. So it starts at -1 and goes to the right. It's going to have a little bit of a funky shape. And again, we have an interval that needs to be bound by the y-axis. And you'll see why here in just a minute, okay? So let's take away those two, and I've gone ahead and prepared these for us. We'll go ahead and we'll zoom in just a smidge, actually a smidge more, and we see this area right here. And it's going to be this area because it's the y-axis and these two curves. Now obviously this is the linear, this is that square root of 1 plus x cubed. Kind of a funky looking graph. Now this area right here obviously is going to have the linear on top on that interval. Now it looks like they go ahead and meet here at x is equal to 2. I can, if I want, confirm that. It wouldn't really be all that big of a deal, but let's just go ahead and pretend that I already have. You can also confirm just by like plugging in, right? So if we go back to the original and we plug in and we guess that it's 2, what is f of 2? Well, f of 2 is going to be 1 plus 8 underneath the radical, or the square root of 9, which is 3. If you go ahead and plug into g of x, 2, you're going to get 3. Okay, so 2, 3 exists on both graphs, so you confirm it just numerically. That means that I'm going to have what? I'm going to have 0 to 2. My linear is going to be on top minus square root of 1 plus x cubed. Okay, and let's go ahead and turn that into a bracket so it is consistent with our notation. Now, can you take the integral of the square root of 1 plus x cubed? You might be able to, but even if you could, you certainly don't have the skills right now to do so. So what we're going to do is we're going to go ahead and plot those into the calculator as well. I'm going to go ahead and plug in the square root of 1 plus x cubed into y3, and I'm going to go ahead and plug in 1/2 x plus 2 into y4. So we're going to have y4 minus y3 when we get to the main screen. Okay. This is one of those ones where we're actually going to have to use our calculator. Actually, let's go ahead and go up here, and we can actually, I'm going to go ahead and show you on the graph how we confirm or how we find points of intersection. Let's go ahead and change our window. Let's open it up to 3 on the x. So there's my radical, there's my linear, and let's say I want to find, that point of intersection right there, okay? Well, let's go ahead and start looking around, okay? Now let's go back to the graph. Oh. Alpha F3. Okay. Okay, well, let's go ahead and, gosh. Okay, let's do, we need to calc. And notice that right here, once you do second calc right here, and calc is right above the trace button in the blue, okay? Hence telling you that it needs to be from the second button. So we see the fact that it's intersect. You press 5, and you go, and basically it's going to put it on one of the curves. So you go up close to the point of intersection, and it doesn't have to be insanely close. You just put close, and that's close enough. And you're saying, okay, I want to find the and that basically tells the calculator, I want to find the intersection really close to these 2 points on these 2 curves, and boom. If you look really closely, I'm not sure you can see it on the video, it actually says it right down here. Okay, it actually says x is equal to 2 and y is equal to 3. Now let's go back to the main screen and let's actually perform this integral. So we need to go to alpha f2, get the integral up, and we're going to go 0 to 2. Now remember, I put in g of x into y4. And here's the thing: if you accidentally got it wrong, you would just come out with a negative area instead of a positive area. So you would just have to, rewrite it on your test paper, but then just take the negative of whatever you got when you plugged it into your calculator. And then we can actually do that, and boom, there we go. That is one where we had to use our calculator, and we got that. And of course, from here, we either truncate or round to 3 decimal place, box it in, and move on to the next problem. So that actually didn't wind up being too tough. Let's go ahead and look at another one. Okay, clear. I need to go ahead and turn both of these back on because those are going to be my functions. Let's go ahead, and you'll know that you're going to need the calculator because there'll be 2 different classes of functions. Okay, if you look at x squared and 4 cosine x, do you really have real hope of figuring that out analytically? And the answer is no, okay? But you can use your calculator in the intersect functionality that I just showed you in order to find those points of intersection. Now, those of you who are observant are looking at that and going, wow, those both look symmetrical. Well, we know that x squared is even, and you should remember from trig that cosine is even, so 4 times cosine is going to be even as well. So you're going to have points of intersection that are symmetric. That's going to help us out because we can actually find the area of half of this and double it. Okay. Well, let's go ahead and find the point of intersection. So it's second calc, intersection. Let's go ahead and go up to this one on the right. Okay, get close, enter, enter. Now, it tells us that the intersection is at 1.201583. Now, the beautiful thing about your calculator is the moment that you calculate that, it has stored it in for x. See, all I did was put x on the main screen. It automatically stores it into x. Okay, so if I want to go ahead and use that value, let's go 2 times the integral from 0 to, and actually, let's go ahead and instead of doing that, let's store that into b. I don't like it in for x. It kind of weirds me out sometimes. But since I'm used to the second limit of integration being b, from a to b, let's go and store it into b. Let's go ahead and go from 0 to b. And I know that my cosine is going to be on top. So cosine minus x squared dx. And that should give me the area of intersection of those 2 functions. And the area is 6.304. Rounded and truncated would be the same for that particular problem. I box it in and I move on. Okay, that winds up being rather straightforward. We'll go ahead and I'll save video number 4 for some pretty nasty ones. And yeah, I think we'll go ahead and call this one quits right here. If you're not particularly interested in the nasty ones, then don't watch video 4. But if you, I mean, obviously, if you walk through the nasty ones with me and you understand them and can follow the logic, then you'll be that much more prepared. So I recommend it, though it's not absolutely necessary. We will, however, be doing one that is with respect to why. So that might actually be a good reason to watch it